I want to do one more Calc 1 problem. These aren't even really Calc 2 problems, just one more Calc 1 problem. And what I want to do is I want to talk about the following application. So this is going to be, if you even want to call it an application, okay, this is one where we'll have some numerical data attached to it. So this is going to rely on a few observations. The first is Newton's second law of motion. So Newton's second law says that the momentum is equal to the mass times the velocity. And if you differentiate both sides, what this actually tells you is that the force is equal to, well, actually, I'm going to assume that the mass is constant. Mass is allowed to vary, but let's assume that the mass is constant, and then the force is going to be equal to the mass times the acceleration. Okay, so the usual F equals ma. That's the what we think of as Newton's second law, but it's really derivative of something a little bit more basic than that. And so the force being mass times acceleration tells us a little bit. For example, if we know that, so Newton's law of gravitation says that if you have two objects, so two masses, say m1 and m2, so you have two objects with two masses, m1 and m2, the force of gravity that's exerted between those two objects has a particular formula, and it's this formula. So m1 times m2, so the product of the masses, times this constant g, now all divided by r squared, where r is the distance between the center of the objects, and then you square that distance. So when we're talking about the gravitation between a person and the earth, we're talking about from the center of the earth to the center of mass of the person, which the person being only 1 or 2 meters tall is not ambiguous. So that's the force of gravitation. That's Newton's law of gravitation. And so what this says is that if we're thinking about gravitation with respect to the earth is roughly spherical, and therefore we can regard the distance from any point on the surface to the center of the earth as roughly constant. And so what this essentially tells us is that we can think of gravity as acceleration here. So if this is our force, I'm really equating these two things. I'm setting these two things equal to each other. But it turns out that our acceleration is just going to be some constant, which we'll call g. Okay, and really that constant depends on the mass of whatever object there is and the distance between the two. But if we take everything to be constant, we can just assume that acceleration is a constant if we stay close to the surface of the earth anyways. And so this is A. And what we can do is we can derive, if we have constant acceleration, then we can derive our velocity function and our position function. The velocity function being the antiderivative of A. Remember that we're thinking of all these as functions of t now. So the velocity is going to be the antiderivative of A with respect to t. And that'll just be, if g is a constant, that'll just be gt plus some constant c. And it turns out that this constant c is going to be whatever the value is of our velocity at 0. In other words, our initial velocity. So if we call v naught v of 0, then plugging this in to get the initial value tells us that we have g times 0 plus c. In other words, this constant c is the initial velocity. So therefore, our velocity is going to be gt plus our initial velocity. Okay, so that's the formula if we have constant acceleration. And if we do this one more time, the position function, which we'll call s, is going to be the antiderivative of the velocity function. And if we anti-differentiate the velocity, we'll end up with 1/2 gt squared plus v naught t plus another constant, which turns out that that other constant, since these are all polynomials, the constants are just the values at 0. And therefore, so if we call s naught s of 0, plugging in 0 to what we have for our equation, we'll end up with just d. So that implies that d is s naught, and therefore s of t is going to be 1/2 gt squared plus v naught times t plus s naught, where v naught is the initial velocity and s naught is the initial position. Okay, and so these are the laws of motions that we have. And so these are going to be useful if we do some sort of, let's do an example I like to drop stuff off the Empire State Building. The Empire State Building happens to be exactly 1,250 feet tall, so I like to use it because it's a nice round number, but it's a real number. And so let's say we drop whatever you want, a bowling ball, a baseball, a penny. Let's just call it a ball. So let's say we drop a ball off the Empire State Building. Okay, so let's drop a ball off the Empire State Building. And what I'm going to do, so again, let me just emphasize that this is 1,250 feet tall. What I want to do is I want to determine at what speed does the ball hit the ground. Okay, so assuming that gravity is 32 feet per second, we're going to determine at what speed. Speed is not velocity, but we'll talk about it. So at what speed does the ball hit the ground? Okay, I promise you that in Calc 1, you had all the knowledge that you need to solve this problem. So what I want you to do is I want you to stop and think about how can you solve this problem, and I'll actually get us started right away. If you want no hints, just pause the video and go for it. And then in the next video, I'll show you how this works. If you want one hint, here's what I'll do. I'm going to draw an amazing picture with a not to scale person dropping a ball off the Empire State Building. I'm going to assume that the ball, this is slightly misleading. Let's say that they lean over and drop the ball so that the ball is exactly at 1,200 feet, 1,250 feet. And what I want to do is I want to think about what's happening at that point. S is going to be the height, and that's going to be in feet. V is going to be the velocity, and that's in feet per second. I shouldn't say equals. I'm being slightly imprecise here, which I need to be more precise. And then A is going to measure the acceleration. Which will be in feet per second. Okay. And so if we drop the ball, we know a few things. We know that the initial height is 1,250. We know that the initial velocity is 0. And then what's our acceleration? So 32 something. The question is it going to be positive or negative 32? And what I want to think about is, think about these in terms of derivatives. A is the derivative of V. If V is increasing or decreasing, we need to think about what that tells us about the sign of A. And likewise for S. So think about starting with the height. The height, if we're going to drop it from a point, the height is going to be decreasing. And so that means that our velocity, for this particular example only, our velocity is going to be 0. It's going to be negative. Well, I should say it's going to be less than or equal to 0, because of course at time t equals 0, it is 0. But then after that, it's going to be negative because that means that the height is decreasing. And I also want you to think about speeding up and slowing down, which is slightly different than acceleration. Acceleration measures the change, the rate of change of velocity. Speeding up, slowing down measures the rate of change of speed. And speed is going to be the absolute value of the velocity. So technically the velocity is a vector, and the speed is the magnitude of that vector. And so here we're just talking about rectilinear motion, just motion in one direction or along a line rather. And I want to think about, is the object going to be speeding up or slowing down? And if it's speeding up, that means that the acceleration and the velocity have the same sign. Okay, so since the ball is speeding up, that means that the acceleration and the velocity have to have the same sign. And since the velocity is negative, so is the acceleration. And so our acceleration is going to be minus 32. Okay, I've done this. This is more than a small hint at this point, so sorry for spoilers here. But I'll leave it to you to finish this problem, and then we'll come back and we'll talk about it.